Thank you. Yeah, so I'm Matt McCormick. I work at a company, we do open source scientific computing called Kitware. And I've just been playing around Docker and using it myself for scientific Python reproducible computational environment. So I thought I'd give an introduction for people who are interested in this and share kind of some experiences, best practices, etc. So why this Docker thing? Why is it relevant to us as scientific researchers doing our analysis? The situation that we're in when we're doing software and computing is that the software environment, the landscape that we live on, is always evolving. So here we have a little visualization of just the changes to the CPython interpreter. And you can see there's just a lot of changes that happen all the time over the years. And as software is always improving and evolving, it's always changing. And so as computers are deterministic systems, the software is always changing. So it's an evolving ecosystem that we try to do work on with. And the problem that we run into often is that the software changes and then what we worked on breaks. So we have this situation often that someone works hard 6 years, 7 years, or 10 years on their thesis work, and then 2 months later a new operating system comes up and then it's broken and it doesn't work. So really, if we want software to have impact, and open source software has impact, and if we want our research to have impact, it has to be reproducible, and it has to be working, beyond the next couple months. So to do that, really, what we want is a reproducible computational environment. And this is sort of a gray area. It's not like a black and white. It's not like you're going to say, this is very reproducible, and that's not. As you get into the nitty-gritty and experience with registers and floating point operations, there's definitely a gray area. But through experience, if you want something to work years down the line, we have to understand that our stack is the CPython interpreter, and the CPython interpreter in turn links to things like C library, and it's built with a given compiler, and you have packages that you use that have specific versions exposing a specific API, and then also those packages usually have C extension modules, again linking to this C standard library. And you have other libraries and executables you're usually using in your analysis outside Python. And all these things have to work together consistently. You have to have a consistent binary stack, at least down to the C library. So we need to get down to the C library. So what are some things that are very good, that are very helpful, but aren't quite good enough so that a couple of years down the line, we can reproduce our computations that we did. Source code, right? It's very good to open source your source code, and in many ways, this makes your work, your algorithm, your code future-proof in that it can always be modified as needed to be rebuilt. But if you give out the source code, it doesn't give you the computational environment. It doesn't give you the Python interpreter, the Python 3.1 that you used, or it doesn't give you how things are configured, or package dependencies, or the runtime environment, and it doesn't tell you the runtime environment. So if you go and look at any package on GitHub, this is the experience I often have. From going from the package to actually using it and running it, there's a big step, and what do you do? Or it's just a lot of work to get there. So source code is good. Package managers and distributions are also good and helpful, but it's hard to find a consensus on the package manager. And even if you do have a package manager, usually the packages you used aren't going to be around 3 years later. And then when you're doing research and you're kind of solving new problems, there's almost always a situation where you're using something that's not packaged, and so you need to bring in something new. And then we also have virtual machines, and virtual machines are also very good tools for a reproducible computational environment, and they are recommended, and in some cases they are the right solution. But in a lot of cases, it's very cumbersome to use them because they're very slow, and they're just in practice, they're just an inefficient utilization of computational resources. They're self-sufficient, but just inefficient. So the new technology that's the hot buzz you probably heard of around is Docker, which is in general this thing called Linux containers. And this is a new tool that the web deployment people are very excited about, but it's relevant to us as researchers for creating reproducible binary applications. And it doesn't solve all the problems, but it's good enough for reproducible computational environment. So I just wanted to go through today and help out people who are looking into this by discussing, giving a basic understanding, trying to get a basic understanding of what it is, and some of the basic concepts that come with this new technology, and then some best practices if you're using it with a scientific Python stack. So what is Docker? A lot of hype and graphics, but let's quickly try to get a basic understanding of what it is. So it's advertised as a lightweight, portable, self-sufficient container. So container, not virtual machine. So the way I like to think of it, by comparing it to things I'm already aware of, is thinking of it as a combination of a sandbox chroot and a copy and write file system, along with a distributed version control system for a binary computational environment. So chroot, how many people are familiar with chroot? Okay, yeah. So if you've done Linux or Unix programming, you may be familiar with a chroot or BSD jails if you're on BSD. So it's really kind of a sandbox, is basic, just the idea. It's a sandbox for doing your computation. And this sandbox, and the way it's done with these containers versus virtual machine, is the difference is that you have these two different diagrams here. On the left and the right, the difference, that's just a summary, you can look at it for a little while, is that on the left with virtual machines, you have a whole kernel, an entire OS for every virtual machine. And on the right, you have a shared kernel, right? So that you're virtualized just down to the kernel level. And you share the kernel, and then every container works on that kernel. And what's sandboxed is this binary execution environment. So here's a little example. So right there, I'm running Docker inside Docker, which is kind of crazy, but a little hello world. And so I just ran a computational environment. And what happened there was it started up, it created an entire sandboxed network environment, a complete binary stack down to the libc like we wanted, and ran that and set it up and shut it down. And the time there was, a second, or in the CPU time is milliseconds. But if you're doing that with a virtual machine, right, that's maybe 10 minutes just to do the overhead of running that. So it's very efficient, and you can use all your cores, all your RAM. They're shared because the kernel uses them like manages them appropriately. So it's like a sandbox change root. The other technology it kind of combines together is this copy and write file system. And so this is for efficient use of your file system. So the idea is you have these layers. Think of it like a layer cake, where layers are stacked on top of each other, and when you write to a new layer, you create a new layer. And this is by using special file systems. There's different back-end file systems that have this feature that can be used. But what this means, essentially, is that the bottom layers that are shared are shared across many containers, and so you end up not using a lot of disk space. And then finally, it's like a distributed version control system for binaries. Think of it Docker like for binaries, like Git is for your source version control system. And you have Docker push and also a Docker hub, which is like GitHub. You can share, push and pull your Docker images. So what you need really is Linux, but there's also an easy-to-use system that works on Mac and Windows that will provide in a virtual machine all the tools that you need. So then some basic concepts. We're talking about this image. Here, image refers to one of these read-only file system layers. And so you can see the images you have available. Their virtual size is how big it would be if you stack them all singly together, but their real size on disk is something different. They have tags, like you have Git references and hashes associated with them. And then a container is when you take one of these images and run it in memory. And there's a PS command that can be used, kind of like looking at your processes on the system. And then if we run and then look at processes when it's running, that will show us the processes running. And then if after I wait a couple seconds and run it again, it's no longer available, but we can see in the past it was running here. And then volumes is another concept to understand. So you use Docker for your reproducible computational environment, and then you can bring in your data that you want to work on and your source code that you want to work on by mounting it as these data volumes when you're working with it. So in practice, how do you use it with scientific Python? So one little gotcha to be aware of is that the portable Docker image that you can ship around, you can archive very easily. It kind of virtualizes your CPU, memory, disk, and network, but it's a portable system that doesn't depend on the local state or system that you build it on or create it on. So it doesn't include local hardware devices, and a local hardware device in this context is also your video card. So it's very difficult or not advised to use OpenGL with it. So what do you do? It just works very well if you're using IPython or Jupyter Notebook, kind of is where you want to use it. And then there's a lot of great base images out there to choose from. The one that's most commonly used is Debian, and that's kind of the officially recommended. If you use that, it's very lightweight, and then a lot of other images are based on that. There's also a very nice IPython notebook one that sets up the network and HTTPS for you, and you can have your own password. And there's other ones out there that are preloaded with the nice package managers that are available. Or you can make your own. You definitely can create your own. So Docker is hopefully a little more understanding. It's this combination of technologies together, something like a sandbox chroot, incremental copy and write file system, and a distributed version control for your binaries. And the concepts we talked about were an image, which is one of these read-only file system layers, a container, which is a writable image that has processes running in memory. That's what a container refers to. And then we have these data volumes where you mount a directory that has your data so you can access it with the computational environment. And then remember that when you're doing scientific Python, it's best you're not going to have graphical context. very easily at least. So it's best to use it with an IPython notebook is what it works really well with. And you can use a packaging system to help of your choice. So if you're really interested in this and you want to get started, there's a great browser-based interactive Docker tutorial to get your feet wet, and then the documentation is outstanding, which I think really has helped the project. We gave a tutorial last year on that used Docker on reproducible research, and also kind of the IPython Docker Hub repositories are good to check out. So thank you for your attention. If you have questions, I'd be happy to do my best to answer them. So yeah, the Docker program itself is a daemon client server architecture. So you have to at least have it installed, and you also have to have the features in the kernel that you're using. So you're going to have a system that was, relatively recent and has the capabilities to use it. But when you're running it, you can just run it as a group privilege. If your user has that group, you can run it that way. I'm sorry? For what?
Like, you need a specific version of the Linux kernel?
Okay, yeah. It's like 3.1 or 2, yeah, I think, yeah.
Anthony?
So what's your opinion or sense, maybe,
Yeah.
of when you might use Docker in a production environment as opposed to using Conda?
I would use them together. I wouldn't think they're maybe... So if you want so what I would really use Docker for is I'm writing a paper, and I want to be able to come back to that 6 months later when the reviewers come back and say this needs some work. And you can use Conda with it if you want to, but anything long term, yeah.
To solve exactly that problem you just described, in some cases, large, not big data, but just large data inputs are required. How well does Docker do with, if I've got 5 gigabyte HSD images or something, and I need those as inputs to my analysis?
So you can either mount the volumes, or you can also, it does this networking very well. So if your data is on one of these specific data hosted network, you have a data server, you could connect to it too. No. So the versioning is definitely in the binaries themselves, and you want to be careful of versioning the binaries, but then you have to figure out some other way to sync the data versions too. It's a good point.
So what's the preferred method to cite a document container? Should I spend the gold with Rails to utilize it? So how's that done?
There's hashes and tags that you can use with it, and when you use it, you definitely want to use the hash and the tag. And citing it appropriately in a paper, I guess, is kind of use the hash and the tag, I guess, is how do I do it. Put it on Docker Hub. Put it on Docker Hub, yeah.
And Travis, you have a question?
I had a question about data. So can you put data in a Docker container?
You can.
If you put that 5 gigabyte of data in the Docker container, just have a 6 gigabyte Docker container?
Okay, yeah, that's a good point. There's also these data volumes and then their versions. So a good practice, and I didn't mention it, is that you can have these data volumes and their versions. So a common practice then, if you have a small amount of data and you want to store it in these incremental images, these Docker images, which build up, is you can create an independent data volume, and then you put your data in there, and then it's versioned, and then you can mount that data volume with multiple execution environments. Yeah, so that's a really good best practice that you should probably use, which came up before.
Would it be possible in the future to Docker run GPU like Google CL?
It's going to be very difficult. Very difficult. It's very CPU right now at least, you want a CPU-only backend binaries that you're using. I have a couple of repositories on GitHub that show how to do that. If you search for Docker Open GL, but then it's specific to the video driver that you use. So,
All right, thank you,
good.
Matt.
Thank you.